Hi. Okay, so this is section 3.2. If you're in the new book, it's on page 259. If you're not, Sam, I hope you can find it. Yesterday, we talked about exponential and logistic graphs a lot. Talked about what they do, what their equations look like, stuff like that. Today, we're going to stick with those same two things, but now we're going to do some modeling with them, which means story problems, practical situations. You'll be okay.
Yeah.
Okay, here we go. The first thing I want to talk to you about is this, it's a version, not a version, but a different version of this. We have, yesterday we had y equals ab to the x. That was our standard kind of thing for exponential, where this was the beginning amount and this was the multiplier we used over and over. And if this number was greater than 1, we had a growth, and if it was less than 1, we had a decay. And sometimes if this were a negative, we had to embellish this a little bit and then work it out so that we could figure out whether it was really a fraction or not. Remember that? Okay. Here is another version of that. Y equals a times 1 plus or minus r to the t, or I'm going to say t for time, because this is usually the case if we're talking about money. So I'm going to change this with t also. It's the same t. It's just that if you'll notice from this one to this one, b has been replaced with something weird. 1 plus or minus r. And does it make sense to you that if this r was a positive number, we would have a growth? And if it were a negative number, we would have a decay? Okay, I need you to focus really, really tight on some vocabulary. This is called the growth factor. In math, when we say factor, we mean something that's being multiplied by something else. Or in this case, the same thing. B is the growth or decay factor. Factor. Because that thing is used to multiply with over and over and over. That's why we call it a factor. And it's very important. It's not just some word we remember to say, nope, it's factor. It's really important. This thing then right here, if we convert from here to here, that is the growth or decay factor. But this piece of it, that's the growth or decay rate. They're different. They're definitely tied to one another. We do not use them interchangeably. Now, it'll make more sense why we call that a rate if we talk for just a few minutes about using this with either growing or decaying money. As I talked to you about yesterday, I said, if you invest money in a bank account, your money will grow. And it will grow if you use this for it, it will grow compounded. If you buy a car, its value will decay exponentially, just like this. This is your initial investment. It's also the initial value of money that you paid for the car. This is the amount of the beginning amount, just like it was here. But if we have, for example, the value of money being invested. So if I say V as a function of time, the value of your money, or maybe people like it better this way, if I write A for the amount of money in your account as a function of time, is equal to, I'm going to give you a scenario here, so it's an example. Let's say you had $10,000 that you got as gifts when you graduated. Anybody got relatives that'll gift them that much? Me either, but pretend. Just pretend and dream for a moment. Okay. So that's the beginning amount. And let's say that you put it in a fairly safe account that grows at 7%. You can get safe stuff that grows at 7%. If somebody tells you they can make it grow at 35%, you better be. That's very risky. Definitely going to be risky. Anyway, all I'm saying, 7%. Then what I put in here, based on this right here, and I know it's going to look weird, is 1.07. You go, where's the plus sign? And the answer is, there's your 1. We're adding 7%. And when you add 7%, you don't put a plus sign. If you got $1 and you add 7 cents, you don't write $1 plus 7 cents. You write $1.07. Do you understand how this is a growth? And can you see the rate? The growth rate right there is 7%. So if you're presented with something like this and it says, what's the growth factor? You will say, careful now, what's the growth factor?
0.07.
No, what's the growth factor?
1.07.
1.07. What's the growth rate?
0.6.
Don't say it as a percentage. What's the growth rate? 7%. What's the growth factor? 1.07. What's the growth factor?
1.07.
What's the growth factor?
1.07.
What's the growth rate?
7%.
All right, we got it? And this would be for a certain number of years because it's 7% per year. They always give percentages from banks, always annually, so T is always in years. We're gonna do the same thing with a car's value. And it's gonna come down. So if you walk off the, you get out of the car lot, you bought this new car, each year that you have it, it will lose value at a rate of 17%. Believe it or not, that's not unheard of for American-made cars. You're gonna buy something made by Japan, it's generally around 12 to 14%. We'll say 17%. Watch this. And let's say that was a $20,000 car, okay? $20,000 car. In this scenario, then, the value, and I am going to use V here because we're talking about value decaying. The value of your car is going to be the original 20,000.
80.83.
Yes. And now it's difficult to see. It's not sitting and glaring in your face like the 0.07 was. You got to do a little work on this. The decay factor is what? Careful.
Minus.
What's the decay factor?
7.
This is the decay factor. Factor.
Oh, it's a factor.
The factor is 0.83. But what's the decay rate?
Minus
17%. And you can't see it glaring at you like this one is, but you got to do a little subtraction. This came about by taking 1 minus your decay factor. I mean, decay rate. What? This happened by doing the arithmetic on 1 minus your decay rate. And that created the decay factor. But you have to do some work, a little bit of arithmetic in your head or on your calculator to find the decay rate. And it's 17%. And notice that this exponential function will decay because this is between 0 and 1. This will grow because it's greater than 1. But there are pieces of it now. We're busting it apart. So we're using this version of it. And the inside here, that's the difference from 1. That's your growth or decay rate. And what results from adding them or subtracting them is your decay factor or growth factor, either one. You understand how that works? All right. So let's try an example out of the book. Example 1 says, tell whether the population model is an exponential growth function or an exponential decay function, and find the constant percentage rate of growth or decay. Very first one says, San Jose, population is 898,759 times 1.0064 to the T. Growth or decay?
Growth.
Growth. Careful now and write it as a percentage. What's the growth rate?
0.64%.
0.64%. With the decimal over 2, it's still a piece of a percent, barely more than 0.5% growth is what we're saying. So you got to be moving decimals appropriately to answer these. Did you all see why it's 0.64%? Okay. Next one is a growth or decay? Decay. What's the decay rate?
1.42.
1 minus 0.9858. Is that what you guys are doing? That's how you're going to find the rate, is to subtract 1 minus 0.9858. Okay. And then change that to a percentage. Do you understand why you're going to subtract that 0.9858 to find the R?
Mhm.
You do?
Yeah.
Okay. And the R is 0.0142, which is what percent? 1.42% decay. That's what you're losing every year in population for Detroit. That's what happened to Detroit when, in 2008, when the Great Recession hit, people weren't buying cars. Guess where cars were made? Detroit. People lost their jobs and had to go somewhere to find new work. So as that population actually dropped and dropped and dropped. Picking back up. All right, number 2. Here we go. It says, example 2 is another scenario, another thing we gotta model with the stuff we have on the board. It says, determine the exponential function with initial value 12 increasing at a rate of 8% per year. That's not very hard. That's where you start. Y equals what?
5. Yeah, 12.
12 times, and they always put a time sign. I'm going to use parentheses. Times 1.08 to the x or t. I'm going to use x. It doesn't matter. It's the time value. That wasn't very hard either. Done with that. Okay, it's going to get not a lot rougher, but a little bit. Example 3 says, suppose a culture of 100 bacteria. What is the 100?
That's
That's A, beginning amount. It's put into a petri dish and the culture doubles. Doubles every hour. We need to write it. We need to write a model for this. It's going to be the amount of bacteria. Bacteria as a function of time, that's what I'm going to write, is equal to 100. How do we indicate the doubling? And the answer is we're going to multiply by 2 every hour. That's your factor used over and over and over is 2. Does that make sense? To the t. So there's our model. And it went right straight back to this. Because our factor that we used over and over again wasn't a 1 point something or 1 minus something. It was always a point. It was doubled. So we're right back to here where b is 2. Do y'all see it? Question asks, predict when the number of bacteria will be 350,000. That's this, the number of bacteria. So we put 350,000. We're after that t. You have no way to get at it. Not till the end of this chapter. What could you do? How do you solve equations that you have no idea how to solve algebraically?
plug it in. Graph it.
And when you graph it, you graph this in one side, this in one of your equations and this in the other. And build a window to accommodate the size of your numbers. See if you can find when, which would be an x value, because that's what this is. This is a time value. See if you can find when it will reach that. So take my glasses off. There we go. Okay. Is anyone actually able to find an answer without just looking at the one in the book?
Yeah.
What'd you get?
11.77
11.77 what? Units?
minutes.
Ouch, that's where you have to go back to the problem, find out how they're measuring time. Every hour it doubles. And so it's going to take not quite 12 hours to reach 350,000. That's really rather incredible when you only started out with 100. But when you double and double and double, those numbers get out of control real fast. You can tell that from the graph of your blue function. Look at that thing climb. And I got mine up to 500,000 a little bit ago. So if you have no way to get at a variable because you haven't been taught how yet, and I'll teach you by the end of the chapter. If you haven't learned yet, and you have an equation you got to solve for something you have no idea how to isolate. Y1, Y2, and find an intersection, but you have to build a window big enough to accommodate everything. Everybody good? Okay, moving along. Now we're gonna do radioactive decay. So this time, we've got a substance that's radioactive. You guys all know what's going on in the nucleus of a radioactive substance? Well,
No,
Shooting
it's
off particles.
splits.
in a stable version of an element, all of its little nucleuses have a certain number of protons, which determines what it is, and a certain number of neutrons, and they live happily together inside, and everybody's cool. And then some neutrons come along and want to make their home in the nucleus, and everybody gets too crowded, and everybody gets mad, and the neutrons begin to fall apart and spew out radioactivity. And what's really cool is that some of those neutrons, which are neutral, they might spew out just their electron. That's called beta radioactivity, beta emissions. But if he spews out his electron, he becomes a proton, which changes the substance to a new substance that may or may not be stable. There may be other neutrons that want to bust apart so they can be comfortable. And sometimes the entire thing that spews out is a helium. 2 protons and 2 electrons. They take off. And you've lost 2 protons and the substance changes. That's called alpha radiation. So the reason why I'm telling you this, I'm not trying to teach you any science. It's much more complex than what I just said, but ultimately that's what it comes down to. The reason I'm telling you this is because a lot of books, especially math books, because these guys are nuts, if you ask me, they haven't taken any science at all. They say, for example, you've got a radioactive piece of carbon, it's called carbon-14, it's got 2 extra neutrons than the stable version does. It's called carbon-14. You got a whole bunch of carbon-14, and its half-life is, they tell you the half-life, and they say, which means that half of it disintegrates. It does not disintegrate, it becomes something else. But there's still only half the carbon-14 left, and the other half has become something else. That's the reason why I wanted to tell you about the little science thing. This doesn't disintegrate or ethereally go off into space somewhere. It becomes something new, usually something stable, but not always. Anyway, and by the way, and I didn't know this until I actually asked Mr. D and then read it, some science articles. There has been nothing, not one thing in all of the study of chemistry and all the lab experiments and all the proton accelerators that we've got, big, huge monster things. No one has been able to change the half-life of a radioactive substance with heat or pressure or speed or collisions or chemical reactions. Those are known things and no one has been able to change them. So if the carbon-14, that's what you use to radioactively date bones that you find. You want to know how old they are? You slice off a little piece of bone and burn it. You find out how much carbon-14 remains. We know that since the thing died, carbon-14 has been decaying, and if you can figure out how much is there now, you can backtrack and figure out how much it had when it died, which is about how old it is. You follow me? And no one has been able to change the the carbon-14 half-life, which is about 5730, 5,730 years. That's a half-life number for it. That's a steady number. Anyway, moving on. Gave you a whole bunch of information about that. Let's see if we can make it work here. It says, suppose the half-life of a certain radioactive substance is 20 days, and its mass was 5 grams initially. Find the time when there will be 1 gram of the substance remaining. Now, I like the way the guy phrases that. Doesn't mean there's only 1 gram of stuff. It means there's only 1 gram of the initial substance. The other 4 grams have changed to something else. Okay, there may be a slight reduction in the weight because of the energy lost. E equals mc squared. A little bit of mass may be lost in the transfer, but it's not, you're not going to lose 4 grams. All right. So let's see if we can take this information. It says that the radioactive substance decays, half-life is 20 days. So we started out with 5 grams. So the amount of substance as a function of time is equal to 5 grams to start with. What's the multiplier we're going to use over and over and over again? Oh, I didn't go through my whole discussion. If you have this much radioactive substance, then after its 1 half-life, it'll have this much. And then after another half-life, it won't go to 0, it'll have half of that. And the next one will have, after the next half-life elapses, you'll have half of that. Do you understand? So what's the factor we're gonna use over and over and over again? 1/2. Now, this is the tricky part in this particular modeling situation. Is it just 1/2 to the T?
No, because every 20 days.
Yeah, somehow or another we gotta get that 20 in there. So think about this with me for a minute. If this were 20 days, that's the exponent of 20 days, then I will have used this once, and this substance will have reduced down to 2.5 grams. If this were 40, I would have used this twice. I'm sorry, not 40. 2 half-lives. I screwed this up. If I had 1 half-life, this would change to 2.5 grams, but it would take 20 days to do it. If this were 2 half-lives, I would have used that twice, and I would have had 2.5 cut in half, which is 1.25. This is 40 days.
How do you know how
Not
many
2
days it
half-lives.
is?
What?
How do you know how many days it is?
It tells you in the problem. Do you know where we are?
Yeah.
See, it says 20-day half-life.
Okay.
Okay. But what if it's 30 days? How many half-lives will have been used?
2.5.
1.5 half-lives. It's at 30 days, and you're like 1.5. So that means that you would replace this with 1.5, which you could do. But what if it's 22 days? Isn't this how many half-lives? If it were 22 days? Barely more than 1, but that fraction? And in this scenario, can't we put the number of days, which we don't know, like that? The number of days divided by 20 is how many half-lives have gone by. Does that make any sense to you?
Because then every 20 days, that'll be like a 1, and that'll be a 1.5.
Yes. So if it were 20 days, that would be a 1, and we've used half-life once. If this were 40 days, it would be 2, and we've used it twice. If it's 30 days, then we have 30 20ths as our exponents. If it's 22 days, it's 22 over 20. If we have 48 days, it's 48 over 20. That's how many half-lives we've used. Does that make sense? Everybody clear on this? That the half-life is the denominator here. Don't memorize a rule. Make it make sense to you. Okay? So then, once we finally figure out that it's T over 20, they want us to figure out how long it's going to take for 1 gram to be left. You're stuck in the same boat you were up there. You have no idea how to get at that T. So don't. Solve it with your calculator and graph it. And by the way, those of you that are listening online and you guys in here, if you do know how to solve for TD algebraically, more power to you. If not, do it my way. You're gonna have to reduce your window seriously, right? Did you build a window where you can see the intersection? How many days till it arrives at 1?
46.
Yep, 46 and a half about, right? Think about that too. It makes pretty good sense because if you cut 5 in half after 20 days, you get 20 days ago by, you got 2.5. If another 20 days goes by and you're now at 40, you're now to 1.25. It's not going to take many more days to get that down to 1. You following? Okay, so that should make sense. Okay, turning the page. Example 6. Are you ready to go on? Or wait, I guess we'll wait for a minute. Those of you that have turned their stuff pretty big in your stat, because we have to do this. I want you to do it, I know it's a pain, but do it anyway. So we're doing example 6, it's modeling US population using exponential regression. So what are you gonna put in your first, when you go to edit, you put it in list 1, what are you gonna put in for your first element in this problem? 0, very good. And then it's going up by what? 10, okay. Now, before you get completely done putting all your data in, we need to read the instructions here that says, use the 1900 to 2010 data. Don't use the 2016 number. That's gonna be used for comparison. That last element there is gonna be used to compare how well we predict using the first one. So don't put the 2016 one in, okay? Just stop when you get 110 in your first column, and then only use all but the last one in the second column. Make sure your list is the same length and your numbers are about the right size. And then, when you've done that, go and build a window that will accommodate the size of these values. I'm gonna go from probably -20 up to
Wait, Miss J,
130. What?
I, like, by the time you said that, I had already put the 2016 in, is there a way to just delete that one number?
Yeah.
How do you, I don't know why.
Your edit keys are, your edit key is right here, so you delete and insert. So what did you wanna do?
Just delete, because now it's just having a 0.
Okay, well,
So
sit on it,
like-
delete it.
Oh, just,
That'll delete whatever element you're sitting
oh,
on. You can also, if you forget an element, you can sit on the one just below it, like if you forgot that this went from 60 to 80, you say, so sit on the 80 and the second insert 70, and you'll put in that.
oh.
So you can, those are your two edit keys. They can work kind of like a computer, but it's a little more cumbersome. Okay, has everybody got a window to set up that they can see this in? I haven't yet, because I'm asking questions, just a minute. One equals, turn off those, turn off flat on. That's off. Are you getting, so you built some sort of a screen where you can see your points out like that, if you turn the flat on and Y1, they look kind of like that? Blue boxes, for those of you on, with something like that, if you build a window properly, you basically be able to see your boxes about like that, okay? All right, so we want to do an exponential regression. Let's go find it. Stat, over to calc, down to exponential, which I think is 0. Put your information in. And I have my diagnostics on. My R squared value is 0.995. That's really good. So this ought to fit really well. So by just visual inspection, it fits pretty well. Okay. All right, so all that crap has to happen first. And then if you look in your Y equals key, you'll see that their population thing, which is 81.2263, is just like ours. And the growth factor is 1.01263, just like theirs, only we got a little bit more up to the X. So it looks like we got the same regression they have. What they asked us to do was to predict the 2016 population and compare it with what it actually was. That's the last value there. So go back to your graph and go second calc, a value where? Where do you want to predict a value? 116, right. And the graph tells us, it predicts that that would be 348.48. What was it actually? 323. 323 compared to 348. You might think, well, that was not a very good prediction at all. It's actually pretty good. With the size of the 300s that we got, the difference between the two isn't all that much. It's pretty, not great, but it's pretty good predictor. Can you think of any reason why the growth all the way up to there, or very, very close to all the way up to there, fit the curve so well? This one doesn't quite fit as nicely. Think about history and what's going on. What? I mean, the population, the actual population, is quite a bit lower than what was predicted.
Because people, oh, I got it. Women started working more and stopped having kids.
That's, well, there's that.
Oh.
And the working more didn't cause them not to have kids. Because, and then you're all adults here, women going to work does not prevent sex. Just saying. So why did population drop, do you think? Didn't cut down on sexual behavior. It did cut down. I mean, there's ways to prevent pregnancy. A lot of people in the new era, if you will, above the year 2000. A lot of people, and I watched this the other day on our news program, it was a half-an-hour thing, very, very interesting. People are turning inward, and they're looking at what's best for them, not what might be best for a family. That's weird around here. We don't get that around here much. Family is everything. Having children is a commandment. Anybody that's outside this region watches this video that we're recording, they're gonna freak out. But we all know what we're talking about, right? Yeah? But for most people, especially in our country, the baby boom is over. We're now having fewer and fewer kids because they're harder and harder to support the economy and things that we have, and people are turning inward of it, trying to make them figure out what helps them survive first. Okay, I'm just saying, that's what's going on. And before that, the many decades before that, people were having families, 5, 6, as around here, 10, 12, 18, saying that, you know, family sizes have cut down quite a bit, mainly because there's lots of ways to prevent pregnancy. And even if you can get pregnant, you can go terminate it. It's just, I'm just. All right, moving along. Take a look at the next one. And I don't want you to actually put this in your calculators because it takes too long. We've got really nice graphs that we can discuss, and I'm pretty confident you could do it. However, there is one thing that I need to show you, to tell you how to do on the next one. What we're going to do is we're going to be comparing the same years, but we're going to look at the populations of Florida and Pennsylvania. You got a good idea in your mind where those are in the country, those two states? Yeah. Better. Okay, so what we're going to try to do is we're going to put two graphs on one screen. Okay, and here's what you got to do, folks, to make that happen. You got to go to the stat plot above your y equals key. So you go to the blue button stat plot, and you got to make sure that plot 1, and if you just did this last problem, I'm sure it's set up right. It's with list 1, list 2, and a box. Can you see that right here? You guys, can you see that right here when you go to the window? Right here at the top, it'll tell you what's organized in there. And according to this, plot 1 is a scatter plot, which is the blue bunch of dots, and then list 1, and then list 2, and then it's going to mark them with a box. What you have to do is make sure that your plot 2 is also a scatter plot. Mine is not. So when you get to the 2 is highlighted. If it's not what I'm telling you, then you got to go into there and amend it. I'm going to have to come back here and make it a scatter plot, a red scatter plot, if you've got a color one. And it should be list 1 and list 3. Because your time elements are still going to be in list 1. But your Pennsylvania populations are going to be in the 3rd list. So it needs to be set up as, plot 2 needs to be set up as scatter plot, list 1, and list 1 is the blue one above the number 1, list 1, and the Y list should be list 3. And you should mark it with something different so you can clearly tell the difference. So I'm going to mark mine with a cross. Plus sign. Okay with that? And when you go to build your window for putting 2 graphs in at once, when you go to build your window, you want to make sure you accommodate all the values, the biggest and smallest population from both states. Yes,
So, plot 3, should that be L1 and L4?
I don't care about plot three, I'm only doing plot 1 and 2. Okay, so if you were able to do that, and by the way, folks, you know when you go to store it, it says store equation in. When you do the one for Pennsylvania, for heaven's sake, store it in list or Y2. Otherwise, it'll overwrite Y1 and you won't have Florida anymore. You know what I'm saying? So when you go to do the regression for Pennsylvania, you will use list 1, list 3, and store it in Y2, not Y1. Y'all follow? Okay. All right, if you do that, then you will get graphs similar to the ones that you see at the bottom of this. You will get 2 graphs, one from Florida and one for Pennsylvania. But what I want you to do is look at the graphs and let's see if we can figure this out, especially the second one. You have to open up the screen a little bit and see what's going on. And this is kind of weird. These are logistics, by the way. You do a logistic regression, not an exponential one, logistic. And that's way at the bottom of your calculus of things. Why don't you go find that list so you can see what it looks like. Go stat, over to calc, and way down at the bottom of the list, at B, it says logistic. Make sure that's what you're choosing when you go to fit the data. Okay? Now we all know a logistic curve looks like this. Starts somewhere up here and then goes up exponentially for a while and then levels off at the carrying capacity, right? We talked about that yesterday. So now I want you to look down at what would happen if I gave you time to do it in the calculators, but I am running out of time here. This is the graph I want you to look at right here. The blue one is Pennsylvania. No, is that right? Yeah, I think. The blue one's Pennsylvania and the blue one's Florida. Yeah, sorry. List 1 is Florida. The blue one is Florida and the red one is Pennsylvania. And they don't really look like, I mean, Pennsylvania's especially doesn't look like a logistic curve. Florida says. That's because Pennsylvania's has its drop down coming down this way before the time where they collected data. So Pennsylvania's exponential growth happened before 1900. It's on its way to leveling out. You see what I'm saying to you? Yes, no? So we're looking at only from 1900. We're not just looking at where they had the same population. I'm looking at the graphs themselves. Why is Pennsylvania almost at its carrying capacity when Florida is at its greatest growth? Florida's greatest population growth happened right there in the middle, about where Pennsylvania's crosses and starts to approach its carrying capacity. It's done growing, but Florida's in its maximum growth rate. And that occurs at around 1940, 1950, right in there somewhere. Why that? Any ideas? We all know Florida as a great vacation destination. It's got beautiful beaches. It's got great big huge areas where cruise ships launch. It's got warm weather. It's got high-rise buildings if you like that. Very well developed. But that's how we think of Florida. That's how I think of Florida. Think of it as a retirement place. I'm not going there, but a lot of old people do. You know? It's cheap to live there and it's warm all the time. You don't have to shovel walks. It's great. What was it like in the early 1900s? Any ideas? And before even. Because before that, there was hardly anyone in Florida before 1900. A swamp. Infested with malaria-carrying insects. Is that what you were saying?
Well, I said alligators. But
Yeah. No, and anacondas and all kinds of big, monstrous, horrible, awful things that could kill you. Swamp cats. I'm not kidding. Big cats that lived in the swamps.
That's terrifying.
It was not comfortable, and it was hot. At least now in Florida, you can get in and out of it in the air conditioning if you want. Nobody wanted to live there. It was a massive swamp. You know where the Everglades are? Florida. You know what they produce? All kinds of dangerous, deadly things. They have brought that under control. They've drained most of the swamp and they've built beautiful things on it. But that's what we're familiar with. And so you're going, how come no one was in Florida in the 1900s? There's no one there. There were quite a few people in Pennsylvania, as you can see. What about Pennsylvania? Why is it done growing in the early 1940s?
Small, so maybe not all the time.
It's not small.
Oh, that's-
Everybody landed there on Plymouth Rock, didn't they? This is where people came over from Europe. They went north. You know why? Because it was more like what they were used to. You draw a latitude line from England over to the United States, it's usually a northern part. And they found ground there and they found seasons there that they were used to, and they knew how to grow crops and stuff like that in an area like that. Anybody that drifted south discovered Florida was not the place to be. And so their growth happened early on in the history of our country and has already flattened out by the time people discover Florida's not so bad if we do these things to it with technology and things that come along. So these are the kind of things you have to think about when you see such a dramatic difference in two graphs, when really Pennsylvania and Florida, they're just north and south of each other. Not that far, they're vastly different. So do you understand what's going on? You gotta think about stuff like that when you actually see the graph. One more example, and I hope you're able to do the two graphs in one. Don't forget to store one in Y1 and the other one in Y2, or it overwrites it and you're wondering where it went. All right, example 6, another logistic model. This is the spread of a rumor. And what kills me about this is, and it's just always, they're never consistent. For example 8, it starts out, Watauga High School. Look at the picture.
Look, it's
Yeah, they're about 6. I don't know why they put that picture in there. Anyway, it's about the spread of a rumor, okay? All right, here we go. Watauga High School has 1,200 students. Bob, Carol, Ted, and Alice, all with different first letters, that's great. They start a rumor, which spreads logistically so that, and they give you the equation right there, that's your logistic equation. Notice the numerator is 1,200, which is the population of Watauga. That's your carrying capacity. It's the most it's ever going to get. This equation models the number of students who have heard the rumor at the end of day T. How many students have heard the rumor at the end of day 0? Don't look at the solution. How would you figure that out? It's 1,200 over 1 plus 39e to the negative 0.09t. Is it 0.09 or 0.9?
0.9.
0.9? So it's 1,200 over 1 plus, what was it?
39.
39 e to the negative 0.9t. Is that what it is?
Yes.
This is the rate. This is how many people at a given day. This is how many people have heard the rumor. So if you want to find out how many people initially heard the rumor at the end of the first day, or day 0, you put 0 in here. What is e to the 0? 1. What is 1 times 39? 39. What is 39 times 1? I'm sorry, plus 1. 40. What's 1,200 divided by 40? 30. 30 people had heard it. 4 people started it at the end of the first day, which is the 0 day. 30 people had heard it. B part. How long does it take for 1,000 students to hear the rumor? Well, this is how many people have heard the rumor. Try solving that for T with your experience so far. You won't be able to do it. What do we do? Do that. Graph it. See if you can actually put that logistic curve in there accurately in your Y1 button. It's not that hard now that we have that cool fraction key, but yeah, you learned about it yesterday?
Yeah.
Okay. The trick to this, using your calculator is an awesome thing. The trick is to build a window. Cool logistic curve. I stretched mine out to 10 days. And you can see the whole logistic curve if you do that. Or you may need to expand it, whatever. So how many days does it take for 1,000 people to have heard it?
5.86.
Okay. So toward the end of day 6. Because that's how they're numbering these days. The end of day zero is the end of the first day after they came to school, starts spreading the room. At the end of that day, that was the end of day zero. So that's what they're saying, that's what they're saying. So toward the end of day 6, 5.86, 6 would be the end of day 6. So towards the end of day 6. Okay, you follow that? You good with it?
Yep.
Good luck. Have fun with it. Okay. All right, there won't be a meeting tomorrow, you guys, because we have a PD day tomorrow, so kids aren't coming to school. So don't tune in tomorrow, but we will see you Monday, and hopefully it'll be at 10:45. I'm pretty sure we haven't got anything to mess that up, so I'll see you at 10:45 or about then on Monday, okay?
Okay,
Okay, thank you.
All right, we'll see you later. Good luck.
thank you.
Okay,
Bye.
bye. Ooh, I gotta end the recording first.